Just a second. Well, A, B, and A, B, C, etc. They're all functions of X, right? That's from our equation. Okay. So then, what is the question? Let me understand the question again. Let me come. Let me just mute you and talk to you in person. Am I audible to you?
Yeah.
Yeah.
It is.
Hello.
Yeah. So that it's your voice is actually cut rate to the काफी ज़्यादा.
Yeah, even your voice is good. Yeah, तुम्हारी आवाज़ कटेंगे. Just a second. Yeah, so let me make sure we understand it clearly.
Sir, doubt यही था कि DX.
Let me repeat and then again ask you to select about it.
Yes, sir.
So let me repeat and then I'll ask you to select about it. Okay.
Okay.
Okay. All right. So. Okay, so see, you have to be careful about identifying the variables. Right? So here, x and y, okay? These are our this and this. These are our independent variables. Okay? Okay, so these are our independent variables, and this is my dependent variable. 2 is my dependent variable. Okay, so these are the remember in actual problems, in application, whatever problems you may have. For example, I have let's say a diffusion equation. So let me just make a side note here. What do you mean by that? That is that, for example, let's say if you have say if I have voice is not clear. Someone is complaining that voice is not clear. Ah, this is. You have to tell the fan that is this any better? Okay, all right. Maybe that was the fan. All right. So so let's say I have a diffusion equation which looks like dt by dt equals to v whole square to the left square, which will be values. Okay, so now here if I just identify, I can identify, let's say x is the same as x, y I can identify with t. Okay, now I introduce another t here. Okay, another t here. This is not a real time. Okay, this is not actually, well, this is not like the real time actually. This is like a parametric variable that you have introduced, I'm calling time life. Okay, so this would be your, so for example, you can call this L, you give any name, okay, does not matter. Okay, so you give it any name. Thing is that whatever variable you call it, and let's call this, let's say S. S is not a good choice. S will, I'll reserve for other notation. So let's call it L. Let's say, okay. So L equal to 0, okay, would mean at uh, uh, set, so you give initial condition, right? So when you have, let's say, uh, you had a bar problem, right? And you have this end and this end, you maintain its temperature, let's say UL and UT, or TL and TT, TL and TR, okay, as a function of small t. Okay, this is something that I can control. Okay, so at x equal to 0, and at x equal to L, so okay, the L is the length. So now here I'm going to identify x with x and y with t. Okay, and t as a function of y. Okay, uh, so sorry, t as a function of x. Let's see. So x equal to 0, x equal to L, t as a function of y is known. Right? So what would it mean is that I can identify, well, the plot is not quite, and in that case, this plot should look like, for example, the orientation of the axis will be different. So let me just show it this way. Okay, let's call this x. And in that case, this would be your t, okay, or y, g. So I'm just using the same notation for diffusion problems. So x identified as x, y as t, and you have at x equal to 0, that means on this line, okay, your dependent variable t is specified as a function of t. That would mean that some kind of, so let me raise this current figure, okay, and we draw this, and at left end, that is x equal to 0, y is given to this is some known function of t, right? Or u is known function of t. So I know that would mean that I know some curve in this yu plane, okay? And then x equal to L, okay? X equal to L, I have another function. So let's say this is my x equal to Ln, okay? And in this plane, okay, I have some other function which may look like this, okay? Which is u as a function of t, okay? So these temperature dependencies are shown by these two curves. Temperature dependency with time are shown by these two curves at the left and right hand. So this would be like a UL, this would be like UR. Okay. All right. And now what I'm saying is, so basically, here in the current problem, this is a second order problem, so I have two conditions given. But current problem we are looking at, it was a first order case, or in general, you can have if you just look at one of the such conditions, what you're doing is you are specifying u, okay, you are specifying this u on a particular curve in xy plane. In this case, this curve happens to be y-axis itself or time axis itself, okay, but it can be any other curve. You could have specified temperature on some xt line, some kind of xt curve, which may lie, some kind of xt curve you could have identified, and on each of these point, on each point of on this curve, you could have identified a temperature, and then you could have given that condition like this. Okay, this is a very valid choice of specifying the initial condition, right? So, or one of the boundary conditions you can say. Okay, so this is like a boundary condition is given on by providing values of u along a curve in xy plane. Okay? Is that point clear? If that is fine, then what is done is now we can at each point. So each point, if you know this point, for example, okay, so if you recall, what we obtained was you know that along certain curves, was it, and let me see. So as long as you can actually let each point, if you know initial values or some boundary values, then you can evolve from those boundary values. You can change x, you can change x, you can change y, you can change u. So these values can change by using these rules, right? So this rule, these set of three rules will tell you that how x, y, and u are going to change. Okay. So basically, that's what gave us a curve in three-dimensional space, right? So we just go back again. Then here, what it's telling me that from each of these points, I can actually form a evolution curve. Okay. So this point, this value as at different x, I can find it like this. Okay, and so on. Okay, so this would be your the way you can find out each point, each initial or each boundary value given here, how it's going to change with as you change x here. Okay, so basically here the t that I'm identifying here, t will be varying along each of these curves. T is a parametric variable which is not to be confused with this t. This t here is like y. Okay, so you can call it L or whatever. When L equal to 0, you have this point, and as L changes, let's say this point moves this way. Okay, so if you go back to our previous result, okay, I could have very well called it L, okay, or alpha or whatever you feel like. Okay, thing is that whatever that variable is, it gets eliminated at the end. Okay, because eventually in order to get the curve, I have to eliminate these variables. Right? So key variables have to be eliminated. Okay? Or time-like variables or the parametric variable has to be eliminated, and after eliminating only you get a curve that will tell me that given initial or given boundary value or initial, these are the same thing. They're basically, if it's a boundary in time, then it's called initial, but in general it's a boundary value, okay, or any value at a given point. So if you know u value at given x and y, okay, I know how it's going to evolve at a later parametric values for which I can independently calculate x and y. Therefore, u can be found as a function of x and y. Okay, starting from that particular value. So that is how you actually. So it's basically like knitting the surface. Okay. So what you've done is now. So what you've done is you had initial curve or gamma curve. I was calling it gamma curve, right? If you recall, I erase that figure. It's the same figure which I had earlier. So this curve is, we're going to refer it as gamma curve. Okay, this is my gamma curve, which is this is gamma curve. Okay, meaning it's basically a curve that specifies u value at over a given xy curve, xy plane curve, okay, which you can choose, and that would be identified with the parameter value to be equal to 0. Okay, I'm calling that parameter as t or time like, but remember that's not actually the real time. It can be represented by any other symbol. Okay, all right, but its behavior is as if it's evolving with something. That's why it's called time like variable. Okay, so anyway, so this is how. So starting with the initial gamma curve. So for example, if I had this curve, okay, this curve, then at from each point I'm able to find another the curve as the time like or the parameter value changes, how those values change, they may change like this. Okay, so depending on how it changes, I can construct a new set from each point on this curve. I construct a new set of curves. Okay, and thereby I construct like a fabric, right? It's basically a solution surface. Okay, so continuously for each point on lying on this curve, I can continuously draw these. I can solve my x, y, u as a function of t. Therefore, I'll get a function. I'll get a function of u as a function of x and y in a given xy along given xy curve, okay, in xy plane, and that will give me a unique curve starting from each such point, and therefore you can actually, when you knit these lines, you actually when you actually combine these lines together, then you actually in the day you kind of knitted the surface. Okay, so the solution surface is knitted. Solution surface is knitted on the gamma curve. Okay, okay. So the gamma curve is where t within quotes, which is like parameter, okay, equal to 0. Okay. That's what I mean by gamma curve. Okay. So to go back again, let me remind you then, probably once again, let's recall what we had obtained was we had obtained that if I have the desired linear linear first order PD in two variables, where A, B, C, and C1 have, you remember what were the how what were the definition, what were the meanings of A, B, C0, and C1, etc. Then these X, Y, and U follow this set of three conditions, right? So this is basically if you along a curve on that particular solution surface, maybe I can write this like these equations are satisfied along the solution surface. In parallel to the solution surface, if you move tangentially on it, these conditions will be satisfied. Okay, and therefore, actually it was said that this vector is actually always parallel to it. I mean, a parallel vector will always point along this particular vector. Okay, so therefore we can construct a curve by tracing that parallel vector along the surface. Okay, and that particular curve on the surface, which is traced by just orienting yourself along this particular vector. Okay. At each point, I know A, B, U, C0, C1. Then at each point, I can orient myself. So, and then I just move in that particular direction, little bit. Again, update my value A, B, C0, U, and C1. I get a new vector. Again, orient myself, move a little bit, infinitesimal small step. Again, see what is my A, B, C0, C1, and C1. Update myself, and thereby I can keep on moving, okay, on the solution surface. Okay, when I keep on moving on solution surface by this way, I will trace a curve on the solution surface. So that particular curve on solution surface will follow these three conditions, these three equations. That is kind of well, this is basically from the form of the vector along which I'm always pointing. The tangential vector on the along that curve is always parallel to A, B, C0 is plus the C1. Therefore, since tangent is parallel to this vector, I can write an equation for a particular curve by stating these three equations, right? So these three equations essentially represent that particular curve that I have traced by keeping myself oriented along V always at each infinitesimal step. If I keep myself oriented along V vector, then I am tracing a curve. repeating myself over and over again. So I'm tracing a curve which is described by these three set of equations, which are the parametric representation of the particular curve. That's all I'm saying. Okay, and these parametric representation of this curve. So, for example, at some point of some value of this parameter t, which I'm calling timeline. Okay, so some value of parameter t, if I know x, and at the same parameter value I know y, and at same value of the parameter I know u. Therefore, it becomes three ODEs where I can consider it to be like an initial value problem. Okay, where for a given t I know u, a given t I know y, given t I know x, I can solve those, right? So x can be found as a function of t, y can be found a function of t, u can be found a function of u and t, etc. Okay, and I will have three equations and four unknowns. I will have 1 degrees of freedom essentially. Well, other way of saying the same thing would be, for example, if I find x as a function of t and y as a function of t, okay, then I essentially know x as a function of y, and u as a t can be eliminated. You can get a function of you can get a u as a function of x and y on that particular curve that we obtained by eliminating t between these two equations. Okay, so all right, so that is essentially the idea. Okay, so is that now let me ask you whether this all makes sense. Does this all make sense? So, isn't the solution supposed to be a curve instead of no? It's a PDEs have a surface. As we started with that, remember you have a u as a function of x and y. This is a surface. Okay, so this represents at each x and y, where x and y are not for arbitrary x and y. Remember, we are x comma y. You have for any x and y. So that means, yeah. So degrees of freedom 1, that will give me one such curve starting from one value of the gamma curve, right? So remember what I'm saying is, if for example x at t equal to 0 given, y at t equal to 0 given, and u at t equal to 0. This is given, okay, where t is a parameter, okay, then I will get a curve, because then I'll get x as a function of t, y as a function of t, u as a function of t. I have three equations, four unknowns, I'll get a curve. So for each such choice, I'll get one curve, okay. That's what I'm saying over here. So each such choice on a gamma curve, okay. So this curve is one of the where I'm given u at a particular, this can be identified with a particular t equal to 0. Okay, the parameter value at along this curve is 0. Okay, so so I have multiple choices of this u as along this curve. Okay, so for each such choice I can get a curve like this is this curve. Let me give a name. These are called characteristic curves. Let me give it a name. Call this characteristic curves. Okay, so this is my characteristic curve, and initial curve is being called gamma curve. Okay, so for each point on gamma curve, I can draw one characteristic curve. Okay? So for each point on gamma curve, which is like having a different 2 points are different, meaning that I have a different initial value. Okay, these numbers will be different for me, x at t equal to 0, y at t equal to 0, and u at t equal to 0. Okay, these numbers will be different if I choose a different curve on a different point on a gamma curve. Okay, so I have two different points on a gamma curve, meaning their coordinates on, or they're basically different points on the gamma curve. And then from each of these two gamma curve points, I can solve x, y, and u. Okay, and therefore get a curve which I'm going to call characteristic curve. Okay, so basically these are my characteristic curves. So this originates from here, this curve originates from this value, this curve originates from this value, and so on. Okay, So for each such initial values specified, I can draw these curves, okay, by solving those three ODEs that I obtained and eliminating t from that. I can get these curves, and therefore I am going to get u as a function of x and y. So you see, essentially what you tell me what I want is you give me x and y, I should be able to tell you what is the value. Okay, so if you give me u any x and y, I can look at this solution, this surface which is formed by basically assembling these characteristic curves, okay, which will form a surface now, okay, and that will be our solution surface. That will serve the purpose of providing you given x and y. Okay, so yeah, we are going to do the example. We are going to do the example. We will do the example definitely. Sure. Uh, so Rohan, is this what was your question again? Then I just re-discussed everything because you had some doubt about dx by dt equal to a or something. So is the your is your doubt persist still there, or I don't know if I really understood your question. I thought you're probably confused about that variable. I define variable. I'm calling time like and time variable. So I thought that was the origin of confusion. That's why I repeated all this discussion. But I'm just asking you again. Uh, did that all make sense? Or you still have wait for 15 seconds for your answer to yes, meaning what? You still have doubt or you don't have doubt? Yes is a very ambiguous thing to say. You have doubt, or is your question, is your doubt cleared or not clear? No? Anyway, you let me know. I'm still not gotten an answer. So you let me know. Let me proceed then. Okay. 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 So basically, what you have is a initial. So let me just try to apply all this to a problem. Let me do the example. That will probably make things better understood. Okay. Okay. All right. Thank you. All right. So okay. Example. So example is very simple example. I have to solve x plus y equal to t. With the condition given 2x comma 0 is equal to x squared. Now let's identify what do I mean by this. Okay, let's just put things in perspective. So you have, let me say, I have x, let me draw the y, red color actually, so that I have x here. Let's say I have y pointing inside and u is this way. Okay, so what is, remember, I have a condition that is given is ux comma y equal to 0. Okay, that is x squared. Okay, but actually in this case it would be better to orient, tutorial it would be better to call this as my x, this is my y, that's my this. Okay, so y equal to 0 is x line. This is my line. So this curve is essentially gamma curve. Okay? So that is given to be x squared. So it is going to look like, for example, maybe I can show this in a different color. A parabola which lying in the ux plane. Okay? This parabola that lies in the ux plane. That is my gamma curve. Gamma x comma y. And remember, gamma is specified over a curve on xy plane. This the curve over which this gamma curve is specified is x-axis itself. Okay? So that is the curve that is general, which may like that. Okay, here in this particular problem, x-axis itself is the gamma curve. Okay, and this function is it's basically it tells me that along y equal to, along this x-axis, I already know that u has this dependence on x. Okay. Now I have to find out u as a function of x and y. Okay. Is this correspondence okay with everyone? Okay. So essentially, what you're going to do is from each point on these gamma curves, you're going to find out, you're going to solve, and basically x is not a gamma curve. This green curve is a gamma curve. It's a gamma curve. Gamma curve is specified over a certain curve. So gamma curve, as I said, as I can read out here, gamma curve is generally specified over certain curve in xy plane. Okay? And you identify some curve in xy plane over which you specify u value. Okay? So you specify u values over certain curve in xy plane. Okay? This is your in general gamma curve. Okay? And here the current problem that gamma curve happens to be x-axis itself. Okay? So here gamma curve is not x-axis. I'm saying wrong. Gamma curve happens to be this parabola. Okay? Gamma curve is defined over the x-axis and this parabola is the parabola. Okay? Given by this equation. All right. So is this all right now? Is that all right, everybody? I'm just teaching. I'm just doing this in a little detail because I don't think PDs have been done. You have done probably PD only to the extent of uh, I guess heat equation is something that you might have done. You might have done separation of variables. Okay, but I think that's the only thing you have done. But this geometrical approach is probably is very important, at least I believe. So that's why I'm doing it. Okay. Okay. All right. All right. All right. Thank you. So now, what do I do first thing? If you go back to our procedure, simply what I'm going to do is I'm going to write it like ux plus uy minus 2 equal to 0. And then I'm going to write it as dot product of two vectors. One has a form of, remember, ux uy minus 1. Okay. So here this would be equal to 1, 1, 2. Okay. That would be equal to 0. All right. So what I know is that my vector, if I point myself always parallel to this particular vector 1 1 2, okay, this particular vector 1 1 2, then I'm actually moving on the surface for sure. Okay. So if I do that, I'll describe a curve, and that curve will be parametrically given by, let's say, this equation. Okay, so these three equations must be satisfied if I am always trying to orient myself parallel to this particular vector. Okay, on the curve. Okay, so but remember, I have to start somewhere on the curve, right? The curve, there should be a starting point. That starting point is given by this gamma curve. Okay, the gamma curve is given there already, and we have to use the fact that at t equal to 0, I have u as a function of x, u as a function of xy, x given by gamma x square at y equal to 0. Okay, that I know that at t equal to 0, I am always constrained to uh, x-axis. Okay, I'm always constrained to x-axis. That means at t equal to 0, my y coordinate is definitely 0, and x coordinate can change. Okay, and when it changes, my u changes according to this rule. That's all. Okay, so so what does that mean? If I solve this, I'm going to get x equal to t plus some unknown constant a. This is going to give me y equals to t plus some unknown constant b, and this will give me u will be equal to 2t plus some unknown constant c. Okay, so this would be your parametric representation of all these curves that you would have obtained, okay, from each point on this gamma curve. I do not know how they look, but I'm just drawing it, just drawing it arbitrarily. Okay, these will be your gamma curves, or these will be your characteristic curves, starting from the particular point on a gamma curve, right? Okay, now, so each of these points will, so now t equal to 0, I know that y is equal to 0, for sure. So if you are this, if you are if you are retained on the gamma curve, and you say that, okay, I'm going to start to construct my solution surface from this particular curve, I know that this must lie on solution surface because it's initial. This is one of the curves on the surface, right? So b is not equal to 0. No, y is b equal to 0. Yeah, right. Sorry, b is equal to 0, right? So at t equal to 0, b will be equal to, I'm sorry. So yeah, that's right. So this would imply at, since I know that at t equal to 0, y is equal to 0, therefore b will be 0. Okay. I know that y will vary like t. Okay. And now, so what I am left with is x equal to t plus a, u equals to 2t plus c. So I have equations like let's see. I have x equal to t plus, is something wrong with my code? Y equals to t. Okay. So u equals to 2t plus c. Right? Now I also know that at you know that let's say at t equal to 0, x is going to be equal, u is going to be equal to x squared. So first, so see, eventually what I want to do is write u as a function of x and y. Get rid of all the unknown things. Here I have t, a, and c to be gotten rid of. Okay, and I have still not used the fact that at t equal to 0, I have u as 0 given by x squared. Okay, so let me see. So let's see, how do we do this? So if you have, I can write these two things together. So whenever I have t, I can replace with y. So x equal to y plus a. That way I'll get rid of t, and u equals to 2y plus c. This is all right. Okay, that's fine. Okay. So now u at x equal to 0, x, u as a function of x. So u at x comma y equal to 0 is given to be x squared. That would mean u equals to, when y equal to 0, this term goes away and I'm left with c, and c should be equal to x squared. Okay, so I have c to be x squared, and at t equal to 0, so I have basically the condition which is c, hold on, so c is equal to and x would be equal to a, right? So that would imply at y equal to 0, x is going to be equal to a, right? So u will be actually, c will be equal to c equal to a square, right? So I have c equal to a square, and I still have one quantity, and we still have that a still left in my equations, right? So you'll be having final solution, which will look like x equal to a, y equal to 0, x equal to, what was that? X equal to t plus a. Okay, so x is equal to t plus a, y is equal equal to t, and u will be equal to 2t plus a square. Okay, so that is why these are my three equations that will describe the answer. So x equal to t plus a, y equals to t equal to t plus a square. Right? So x equal to t plus a, y equals to t, and u equals to 2t plus a square. If you look at this, now just check at t equals to 0, x can be anything. Okay, so that is fine. So that anything, whatever value of x you choose at t equal to 0, that has to be identified with a. Okay, at t equal to 0, y is 0, fine. And then at t equal to 0, I know that whatever x I have, that is identified with a. At t equal to 0, I'm getting u equals to a square, therefore u is equal to x square at t equal to 0. Okay, so initial condition, initial gamma curve is perfectly satisfied with these, and it also satisfies our differential equation, ODEs, three ODEs. So these three essentially give me the solution curve. So a is an arbitrary number here. A may be arbitrary, but the curves would be given by how do you get the curves? Well, that so actually the closed form solution. Closed form solution of this one. Okay, closed form solution would be obtained by getting rid of t and a. So I have three equations. Okay, so I can get rid of t and a. Let's see. So a is going to be equal to, so t is definitely equal to y. So now to get u as a function of x comma y. Okay, the closed form solution, not the parametric form, but the closed form of the solution. What I need is need to get rid of t and a. Okay, so how do you do that? Well, t is wherever t you can substitute y. Okay, and a you can substitute by, so you can see from these two I have a equals to subtract x minus y, so a is equal to x minus y, right? So x minus y will be t plus a minus c, that's it. Okay, so a is x minus y and t is y. So u will be given by 2t plus a square, that would be 2y plus x minus y square. Okay, this is your closed form solution, and this would be your actual function, the right hand side function, u as a function of x and y, that would follow your differential equation. You can check that. Let's see what is ux. Always check. Ux is going to be equal to 2 times x minus y, and uy will be equal to 2 plus 2 times x minus y into minus 1. That is 2 minus 2 x minus y. Okay, so ux plus uy is going to be equal to 2. So this is satisfied. And check the condition given u at x equal to 0, u at x comma y equal to 0. What do I get? That is equal to y is equal to 0. So this term goes away, and it gets x squared. That's another condition that has to be that needed to be satisfied. So these two conditions which were imposed. Basically, one is the differential equation itself. Other is this boundary condition. These are perfectly satisfied. Okay, and so you see that this is a very simple method of arriving at the solution, which has geometrical basis, and therefore, uh, what is that equal to? No. Why? No. It's a general solution. See, at t equal to 0, it's not at t equal to 0. Why do you say that? Because this is my equation. These are three of my equations. These are my equations. There's no t equal to 0 involved in these three relationships. This is for any t, and I've used these three equations to arrive at here. And so there is no x square equal to a square. X is equal to a square. Well, that is at t equal to 0. Of course, I use that at t equal to 0. At t equal to 0, let me sort of the confusion. Okay, so at t equal to 0, what did I do? At t equal to 0, I know that x is equal to a. Okay, and therefore u has to be equal to a square, right? So u has to be equal to x square equal to a square. But I also know that u has to be equal to c at t equal to 0. So all I did was establish the fact that c should be equal to a square from the c equal to 0 condition. That's all. This relationship, this equality was established. I found c in terms of a by implementing the t equal to 0 condition. That's all I did. I'll repeat. T equal to 0, I know x has to be the same as some number. X, whatever the number at t equal to 0 at x is, I'm calling that a. That is evident from this relationship, right? A is, what is a here? A is the value of x at t equal to 0, right? So a is the value of x at t equal to 0, which is given from this relation. So I know that, so say, look, I'm looking at the t equal to 0 condition, I get x equal to a. Now, having seen x equal to a, I also know that u is equal to um, 2t plus c from my differential equation solution, which would give me u should be equal to c. So at t equal to 0, I know that u c and x is a. But I also know that I have to lie on the gamma curve. Therefore, I have to lie on this curve. Okay. So this would mean that my a should be equal to c square. Sorry, c should be equal to a square. That's all I'm doing. I'm not. Is that all right, Rohan? Is this all right? So this I've just established C and A relationship. I've not done anything else. Then having B is already 0 because I know that t equal to 0, y is 0. So I have found B equal to 0. So I have only one unknown parameter left, which is x at t equal to 0, which can be anything. Depending on that value of x at t equal to 0, I can find y and u. Okay. So that is what I've written here. That's all. So x t plus a, where a can be anything. Y is t because v is 0. U equal to 2t. Okay, just a second. Okay, just a second. I'm muting you. Am I audible?
Hello.
Yeah, tell me.
Yes, sir. Uh, sorry, just say x equals to a to 0, right? So when we define the general u, so t is not always equals to 0. So how can we take x equals to a there? We have to take
What?
a equals to x minus t only, no? Suppose when we 0, that is y equals to 0 as well. Then x is equals to a. So when not at t equals to 0, u equals to c, that is x square. So we replace x square as a square.
Right. I did not replace. Well, I know that x equal to
But
a.
that is x square is only equals to a square.
You are missing things up. I wrote x square equal to a square because I'm looking at t equal to 0. Right? I am writing this thing because now I'm using equal to 0 condition over
Yes,
here.
sir. Yes, sir. Equals to 0.
Right? But I also know that t equal to 0, u is c. Right? From here, I know that u
Yes,
is
sir.
c at t equal to
Yes,
0.
sir. That
So I know
is
that, therefore, hear me out.
t0
Therefore, I know
and
that c is
u
equal to a
c
square.
or
C has to be equal to a square, right or not? Just answer me this. C has to, irrespective of where you look at, C has to be equal to a square or not? Answer me that. C has to be equal to a
yes, sir.
square
Yes,
or
sir.
not? That's all I'm doing. That's
Achha,
it. I don't want any.
c
That's all I'm doing. C has to be equal to a square. That's all I'm doing. I found B to be 0, C to be a square. That's all. That's all I substitute over here.
but
0. Is this all right?
yes.
Yes or no? Yes or no? Hello. Is this okay now? Okay, all right, all right. Okay. So that's all we are doing here. Okay. All right. So now, okay, so this is uh, now one. So the simpler version of the same problem is probably we'll use that result later. Also, let me just quickly state that also. So that is ux plus uy equal to, let's say that is 0. Not, it was 2 earlier. Let's say it is 0 now. So you can see this by, so now here I have ux, uy, what was that one? Minus 1, right? So ux, uy, and uh, minus 1. Okay, so minus 1, and here I'll have 1, 1, 0 dotted with this. I'm just equation in this particular form. Okay, and so this is like maybe a simpler ODE where right hand side is 0 instead of 2. Okay, and this I'm just mentioning it, this I'm just discussing because this result will be used later. Okay, so some general result is obtained here. So now here what do I get is dx by dt equals to ux plus 1, ux by dt is 1, y by dt equals to 1, and du by dt equal to 0. Okay, what it's telling me that, remember I'm changing t simultaneously, right? So it's telling me that if I change my t such that these three conditions are simultaneously satisfied, I'm actually moving on this, moving parallel to this vector, right? So this tells me that as long as these two conditions are satisfied, this one and this one will also be satisfied, right? So which tells me that u is a constant, okay, as long as dx by dt is 1 and dy by dt is equal to 1, which in combined form I can say that dy by dx equal to 1. Okay, so it tells me that if I can choose a curve in xy plane such that I have dy by dx equal to 1, that would mean that it's basically looking at a set of straight lines, okay, which is the slope equal to 1. Okay, so that would be, okay. So if you have a set of straight lines that have these straight lines, slope equal to 1. Okay, so on these lines, u will be constant. Okay, so it tells me that u will be constant on these curves. Okay, so we'll utilize this result later. This is another important conclusion that can be drawn from this simple geometrical analysis, that u will be constant on these lines. Okay, so for example, if you were given some kind of gamma curve, let's say, okay, and for each point of the gamma curve, you move along these lines, okay, then you will just carry that value on the gamma curve, that remain the same. Okay, it's like that gamma curve is translated. For example, let's say I had some gamma, let's say for the sake of argument, same kind of some kind of gamma curve that is given by some kind of curve in, let's say, this plane that looks like some kind of parabola. Okay, so now this, let's say this point, if I move this way, it will remain the same value. This point, if you move along the parallel to the x y equal to x, this y curve lying underneath this, so each point, if I move so that dy by dx is 1, I'm going to get the same value of u. That means u will translate this way. The height of the curve, height of the point, which is value of u, is not going to change, right? And similarly here, So therefore, I'm going to get basically this. You can imagine the surface would look like a surface of translation, which you can obtain by just moving this particular parabola or initial gamma curve. Right? This will be surface of translation. So that is another thing which we will talk shortly. Okay, now there's a question. Why isn't the satisfaction of all three equations necessary? It is. Where it's not necessary. Amit, I didn't understand your question. Which part you are referring to? They are always necessary. All the three equations have to be satisfied. When did I say they are not necessary? Amit, uh, you x and y. Three equations. I don't understand what your question. Which equations you are talking about? You said there are three equations. I suppose you're talking of these three. You're talking of these three. Uh, Maybe these three equations, these three ODEs, right? These three ODEs, this and this one, du dt. Yeah, so they are all necessary. Are you referring to the current problem or general relationship or the previous problem? Current problem. Okay. So here also I'm saying the same thing. So I'm saying that when you change t, all these three have to be satisfied. Absolutely. I never said no. So I'm saying that all these three have to be satisfied, which will mean that u is a constant when these two are satisfied, which would mean that dy by dx is 1. That's what I'm saying. U is constant as long as dy by dx is 1. All u is a constant means this is satisfied, dy by dx is 1 means these two are satisfied. So where am I saying that the only two equations are satisfied? No, I'm not saying that. Okay? Yeah. So saying that u is constant, this is satisfied, but remember these two have also been satisfied in order for this to be satisfied. These two have to be satisfied as well. Therefore, this is satisfied when dy by dx is 1, which is implied from these two equations together. That's all. Okay. All these three have to be satisfied. Okay. Okay. So I guess that is about first order linear PDEs. I guess that sets stage for further discussion. I'll not go any more than that. So second would be second order linear PDEs. Okay, and I'll just introduce it and then we'll wind up. So here the form I'm going to write is so second order. Therefore, I'll have two derivatives present, and I'm going to write it like this following form. Okay, I have a uxx. Now I have derivatives which are present, can be mixed or unmixed derivatives. There can be so highest order is 2. That uxx would mean del square u by del x square. Uxy would mean del square u by del x del y, and so on. Okay, and these are the first derivatives. So these are the first derivatives. These are the second derivative terms. Okay, and this is of course not derivative terms. This is a function itself. This is a constant. Okay. Well, constant meaning not dependent on the function. It can be functions of x and y. Okay, but it does not depend on the dependent variable. Okay. All right. So now it turns out, so such equations. It turns out that terms of second order derivative determines the general nature of the solution. Okay, so meaning what I mean to say is that these three terms pretty much decide some general features that you may expect from the solution. These three terms only. Okay, so the linear terms do not affect some general features of the solution. Okay, So this is called principal part of the equation. Okay, so they determine some general feature of the solutions. Okay, and what is done is, I'll just first tell you the result. There's a parameter, there's a quantity which is given by b square minus ac. Okay, if you take this number b square minus ac, then its value of this, the sign of this determines the actually sign of this quantity is used to classify the nature of the PDE based on the nature of the solution. Okay, so what I'm saying is, so for example, if b square minus ac is greater than 0, it is called hyperbolic PDE. Okay? If you have b square minus ac equal to 0, this is called parabolic PDE. And when this is less than 0, it's called elliptic. Okay? So, and hyperbolic PDEs and parabolic PDEs and elliptic PDEs, they will differ in terms of some general properties of the solution. Okay, so there's some very characteristically different. Characteristically, I mean, there are some the solutions have some very general features which are characteristically different from each other. Okay, so we'll look at those later. All right, look at those in the next class. All right, so I guess time is up today, and I'll stop the class. Any questions? Any further questions? Amir, you misunderstood. Now you understood, or you still, or you're just looking at your last comment. Are you fine now, or okay? Okay, all right. Keep it. All right, then I'll see you. We'll see you tomorrow. Bye bye.